Good morning, everyone. We've got a fun day in store for us today because the next class is the quiz. So, because of that, I'm going to keep scrolling and scrolling through the lecture until we get to our next major topic, cost functions. Some basic coverage of cost functions will be on the quiz. So the plan for today's lecture is to first yap at you up to the cutoff point for Friday's quiz. I'll make it clear when that happens. Then I'm going to talk about the assignment that will be posted later today. And then for the remaining time in class, I'll do these examples that I skipped through. So yeah, cost functions. You might be familiar with this wacky thing called computer code. You might have worked with it in every other comp sci class you've taken. And now, finally, this course is going to start looking a bit more like a comp sci course. What we're concerned with, however, isn't really the act of writing code itself, but evaluating how good code is. Specifically for this course, how fast is it? One naive way to approach this is to start a timer. Press start when you start running the algorithm, and then press end when it's completed. But that is problematic because every computer will run the algorithm at a slightly different speed. Even better, the same computer running the algorithm multiple times will get different results each time due to factors like whatever your operating system tends to be doing in the background. You'll learn about that in the operating systems course if you take it, and what other apps are running. Because of that, we want a more precise way to measure this sort of thing. And we'll do that by looking at the code of the algorithm and then expressing how many operations it performs as a function of its input size. This is a precursor to the really good stuff, the stuff that they'll ask you about in a Google interview, called asymptotic notation. No one in the real world really uses cost functions directly, but you need to understand cost functions in order to understand asymptotic notation. You could do this yourself if you want to. Try and work ahead while I'm yapping, but you might not know what exactly this question is asking. This is going to be our sort of first attempt at measuring the speed of an algorithm, where you could say our 0th attempt was using a simple timer. We're going to count the primitive operations that this algorithm does. A primitive operation is loosely defined as anything that your processor can do in one cycle, even though, as you'll learn in Comp 2280, 3370, and a bunch of others, that is hardly a rigorous definition. We're not actually going to do this. This example is to show how crappy and clunky that approach is. But I'm going to attempt it anyway. So addition is one primitive operation. Variable reading is another. And variable assignment is another. Here we're reading two variables, multiplying them and assigning them to another variable. So that's 4 operations. Here we read again and compare. Note that using a constant doesn't constitute a primitive operation. that's a detail you'll find more about in Comp 2280, where literals or constants are sort of embedded into the instructions your processor is taking, so it doesn't have to do any memory operations to work with them. Here again, we're reading, doing an operation, and writing. 3. Now it's for the really hard part. That's 12. Phew. And there we have it. This algorithm takes 12 primitive operations. Wasn't that fun? Now that required me to look pretty carefully at each individual line of code. Oh yeah?
Why does branching not count as an operation?
Ooh. Let's see. Yeah, the student's wondering why this if doesn't count as an operation. And I think that's because we already counted the comparison as an operation, and then that's ultimately kind of an implementation detail of the whatever processor we're using. I think it's a really good question, but the answer ultimately won't be that important because of how we're going to streamline this process. So short answer is doesn't count because we already did this comparison. Three, 4, 2, 3. Wow, I actually got that right. When I was reviewing these, I would keep getting these wrong, and again, that's fine because we're not actually going to do this. Processors are really fast. The difference between one primitive operation and 2 primitive operations really isn't meaningful. It's like a couple billionths of a second. So we're going by, yeah, and it turns out the amount of time, the measurement of the amount of time that this algorithm takes wouldn't meaningfully change if we just went like 1, 1, 1, 1. All of these are constant time. This is our, second attempt at measuring time of an algorithm, and I think we're going to have at least 3 attempts. We just lump all lines that contain only primitive operations into one step. Later on, we'll see stuff like loops and function calls, and then those are going to have a number of operations that's variable based on the algorithm's input, and that's what we're ultimately going to care a lot more about. Warm-up exercise part 2. This takes 1 step because it only contains primitive operations. This takes 1 step because it only takes primitive operations. So does this. You can take a wild guess at what this does. It's 1. Incredible. Also, in cases where we don't know the value of, say, b, we would have to pay a bit more attention to the branching. You might remember piecewise functions from calculus. You would use those. But that won't be too important right now. Oh, yeah?
So, it's more than one operation? Can you just summarize that for 1?
Yeah, because we'll find later, actually pretty soon, that loops are what really causes or accounts for the majority of the time taken by an algorithm. So we will be more precise about loops, but individual lines of code that always take the same amount of time to execute, yeah, each line is one step. All right, this is exactly what I was just talking about. We're going to use summations, as discussed yesterday, to evaluate the cost of a function that uses a loop. So let's see. This takes one step. This takes one step. And now we're going to have to think a little bit harder. K starts at 1. I'm going to draw it, here. So it starts at 1. Thankfully, it increments each loop iteration. So in a more complicated loop, you might have to do some more fiddling around with the code before it can be expressed as a summation, but luckily it starts at 1 and counts up by 1 and goes to n.
Would be n plus 1 if it's while it's less than or equal to?
Let's see. I don't think so.
Right.
It starts at 1 and then the loop will terminate when k equals n plus 1, which might be what you're thinking about, but we'll handle that in a different way. We're still just going to have n up here. How should I draw this for now? I'm just going to lump the whole loop together as one thing. Say that each of these operations take one step. So 1 plus 1 is 2, and 2. One more detail that I think addresses a question that was just asked. Each loop iteration, it'll check the loop condition, then if it's true, do the stuff inside the loop. If it's false, exit the loop. That means that if the loop takes n iterations, it'll execute everything in here n times. It'll check the loop condition n times. But then at the end of the loop, it'll check the loop condition once more for the algorithm to figure out that it should now exit the loop. Because of that, we have to add 1 to the number of steps that the loop is taking. So as a function of n, the count for this is 1 plus 1 plus a sum of k equals 1 to n of 2.
Why is it a 2?
Because there are 2 steps within the loop.
Does it also check the loop constantly as well? So
Oh, true. It would be 3. Thanks. And then we'll simplify it. There is one more step for the summation identity, but I'm pretty sure this is just 3n. And I think that's it for the quiz, actually. Okay, yeah. Later on, we're going to talk about more complicated loops. But this sort of thing is what we'll talk about for the quiz. Cutoff is slide 24. And you'd better be able to analyze a simple algorithm like this for the quiz. Hint, hint. There might be a question that looks pretty much identical to this, maybe, but who knows. Next up for today's plan was the assignment. The assignment is almost completed. I just haven't made the solution for the last part of the last question yet. And as I make the solution, I find corrections in the question. So even though this PDF file exists, I don't want to post it quite yet because I'm probably going to end up posting another version of it 10 minutes afterwards and have it be out of sync. So I am going to post it today, and we'll go through it in class briefly right now. This assignment is mostly theory with a bit of coding mixed in. You can read this yourself. Question 1 is to write a written mathematical statement in logical notation. So this will look something like, for all integers, blah, 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 there exists, blah, 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 even. Don't want to spoil it. Don't look at that. And a big chunk of the assignment will just be proofs. These first two are these two are glorified true or false questions. I don't guarantee that either of these are like correct statements that are true in math. That's your job to figure out and then either prove or disprove it. These two, however, are definitely true, and they will better resemble what we've done in class. So it'll involve playing around with inequalities, guessing and checking values for m and n, that sort of thing. Then finally, some actual coding. This is the one that I most wanted to talk about in class because the purpose of this question might be a little misleading. The actual code that you're writing isn't that important. This is just an exercise in implementing a couple of functions from statistics. You'll write a program that calculates the mean of a data set and its standard deviation. And it'll get the data set itself from a file. And that's more the important part. In future assignments, you'll be writing much more complicated programs that take files as input. And this is sort of a practice, like warm-up assignment for the sake of making sure you know how to read files in a program. Dr. Vaughn calls this, because she had a similar assignment in her version of the course last fall, she calls it the can you follow instructions assignment, because most of the marks for this come in making sure it works as we say that it should. yeah, you even get the code. Like, the coding is not that important. Then after that, you'll do what we just did, analyzing time complexity of these algorithms. So you'll do something very similar to the example that we did just now. Look at these code snippets and tell me how many steps it takes as a function of its input size. The notion of having a function of its input size will be a bit clearer as we do more examples in future days. This isn't due for a couple of weeks. But in this case, the input size, n, is the number of elements in the data set that you're given. Yeah, this makes me want to go a little off topic, but still very much talking about the course. We saw in something like this algorithm, where we had a simple loop and a bunch of primitive operations, that we got some constant amount of primitive operations and a loop that depends on n. In the real world, running functions like this, n is going to be huge. Like, you could imagine writing code that works on customer data for a decently sized company, n could be in the thousands. And thus, in a function like this, that 3 isn't really important. If we counted primitive operations, we might have gotten something in the tens, hundreds if it's really complicated. But the overall time or number of operations or steps, whatever, that the algorithm takes would still be dominated by that for loop, that part that depends on n. So, like I said earlier, this will be clearer as we do more examples. You're just learning about this for the first time, so it's okay to be confused. But hopefully that illuminates why we sort of glossed over the number of primitive operations that any given line in an algorithm does. It's because it doesn't really matter once you have a realistic scenario with a loop being repeated many, many times on real-world data. So that's the assignment. I believe it's due on the 31st. Sure is. Any questions about it? Cool. I'm sure you'll have many questions once you start. Office hours and my email are I was going to say always open, but they're not. You can come to me during my scheduled office hours or email me anytime. And also take advantage of the UMLearn discussion forums. As discussed in the syllabus, there will be a forum for this assignment so that I'll essentially be able to ensure that each student has the same amount of information about the assignment. No student will get like insider information by asking a particularly good question. So if you have any questions about the assignment, use the forums instead of an email. Now that we've got those more urgent things out of the way, let's go back to quantifiers. Where even was I? Oh, there we are. last time we did this one, and you remembered this bit of rough work. And I'll start this bit of the lecture by just sort of reading out the slides that came after, because they contain some useful exposition on what was going on in that question. This point's important. In the actual thing that you hand in, you don't have to show how you determined n. You can just say it and pretend that you were genius level enough to just go like, looking at that question, I think it should be a maximum of 2 over m or 2 plus 1. And also, the expression we used was not the only possible choice. In fact, we found 2 possible choices because of this little bit. We found in our rough work n should be greater than maximum of root 2 or 2 over m, which would lead to a formal proof saying that it equals that maximum plus 1. But the thing in the slide said that, or it used 2 instead of the square root of 2. Those are both correct. The inequalities involved still work when we have either of those values. This slide shows the general technique used here. Similar to previous examples, we have an inequality that we want to choose, or that we want to prove. One side is simple because it contains only one term, but the other side contains multiple terms, which is difficult to compare with the other side. Like, we want to solve for n in our rough work, but that wouldn't currently be possible. So we want to make the complicated side simpler, making it just one term. And we also want to make it smaller in order to be in between the 2 sides of the inequality, so that the logic with this chain of inequalities and the simpler side, or the simpler version being true leading to the more complicated version being true, for that logic to work. So we factor out the highest power of n on the big side, and then choose n. This is the tricky part. Choose n such that the terms inside of these brackets evaluates to some positive constant. In this case, we chose the square root of 2 so that n squared could be greater than 2, and then 1 minus 1 over n squared could be greater than 1/2, and then boom, we had one term. And from there, it becomes much simpler. You can do familiar algebra to solve for n there. Another point worth pointing out is that this process gives us 2 conditions on n. We found one condition by guessing a value of n that would turn this whole expression into a constant. And then we found another condition by solving for n from that simplified expression. And what I mean by condition are that, in this case, n had to be greater than 2 over n, and n had to be greater than root 2. Those are what I meant by conditions. And then we get a number that's greater than both of them by saying that it has to be greater than the maximum of the two. All right, let's do another example. This one's kind of tricky because both sides have two terms. So we'll have to do something to simplify both sides and have a simplified inequality that sort of exists between these two expressions. And also, these are fun because I could just show the solution plainly and it doesn't really explain how to solve the problem. But let's get into what thought process you would need to get max of 6 and 4 over m plus 1. I'm going to worry about this side first. It's a bit easier to work with. Come on. And I'll sort of illustrate again, this notion of having an inequality that exists between two expressions. N squared plus 6 is less than some sort of less complicated expression that we get by manipulating it, is less than some other less complicated expression that we're going to get by manipulating this side of the inequality. And that's less than the original big side of the inequality. So we're going to show that n squared plus 6 is less than something, and we're going to show that m times n cubed plus 5n is greater than something. And comparing those two new simplified expressions will show that the original inequality is true, just by how it's all arranged. Yes? Okay, so I can answer that second question pretty easily, but just to clarify, what did you want me to repeat the explanation of?
When you're writing n squared plus 6 something.
Okay, so the reason why we have two mysterious expressions is because, well, as you know, in previous examples, we just had one, and that was because one side of the inequality was complicated. This side had two terms, so two expressions separated by addition or subtraction. So we wanted to change that into something simpler. This expression just had one term, so we didn't need to do anything with it. Now, however, both sides of the inequality have two terms and are thus difficult to solve for n with. So because of that, we have to make simpler versions of both sides rather than just one of the sides. Although I'm realizing now, while we're still going to continue with that strategy, you may be able to get away with only making one simplified version. If the simplified version of this side of the inequality was n raised to some power plus some constant, and that constant was plus 6, you'd be able to subtract 6 from both sides to get a nice one-term expression on both sides. But you'd have to get pretty lucky for that. So we're just going to simplify both sides. So now what? We want to find some expression that is greater than n squared plus 6 and only contains one term. And we're allowed to make any assumptions about, oh yeah? Let's see. Sure did. Thanks for pointing that out. Keep getting collateral damage with this eraser. Anyway, we're allowed to make whatever assumptions about the values or bounds of n along the way, as long as we write them down and eventually put them into the conditions that we introduce into the formal proof. So I want to keep n there in order to solve for n eventually. I just want to get rid of this pesky 6. So I want n squared to be greater than 6 then. Which evaluates to n being less than square root of 6. And if we have that condition, then we have that n squared plus 6 is less than n squared plus n squared, which is equal to 2n squared. So now we have one of our simplified expressions. That's going to be n squared plus 6 is less than 2n squared is less than something is less than this thing with m. Now, be careful about the exact inequality signs when you're doing this. Because we're starting with m squared, or starting with this expression, and want to find something that fits into here, we're going to want to find something that it's greater than, rather than the less than signs we've been using this whole question. But before we do any actual inequalities, we're going to use that factoring out trick described earlier. We're going to factor out n cubed to get mn cubed times 1 minus 5 over n squared. Now it's time to guess and check a value of n. We want a lower bound for n, meaning that n is greater than some value. And that lower bound should be positive. Those conditions are both just to be consistent with there exists n greater than 0. So we want to find such a bound that makes 1 minus 5 over n squared equal to some constant. My best guess is that 1/2 is a really convenient number to subtract from 1 because you get 1/2 from that. So I want confusing myself with inequality signs. Okay, so I think we want 5 over n squared to be less than 1 over half. Remember, this 1 over half is purely from my guesswork, and there can be many different values that also work for this. So I think we can just solve for n, yeah. I'm going to put a big old question mark because that's sort of my convention for saying that this is part of a guess in rough work. So if we set n greater than root 10, then 5 over n squared is less than 1/2, which means that 1 minus 5 over n squared is greater than 1/2, which means that the whole thing, I'm going to write this down in multiple steps just to make it clear, but eventually we're going to get a nice one-term simplified expression that'll look like 1/2 mn cubed. I think I've said a couple times before in the course that you should err on the side of having too much detail than too little. But the exact amount of detail that you should put in is a bit of an art, and you'll develop taste for it over time. In this case, I think the markers would be fine if you just went directly from that step to that one. They can do this algebra in their heads. But if you do all that algebra, then you certainly won't get any marks off. Yes?
Why do we have plenty of plug in? And then we just said do the other end.
So that we could get an expression that's in terms of n. If we put our value of n into the other instance of n, we would have gotten a constant multiple of m, which wouldn't help us in our quest to get a value for n that completes the proof. I do admit it is a weird way to write and think about this stuff. Manipulating inequalities is a skill that they don't really teach you in calculus courses, at least when I took them. But yeah, you can totally plug in variable values for only certain instances of those variables if it gets you towards the expressions that you want. Let's finish off by solving for n. From that bit of algebra, we got n must be greater than 4 over m. And there we have our 3 this time, conditions on n. Oh, plus 1. But since square root of 6 and square root of 10 are both constants, and square root of 10 is obviously larger than square root of 6, we can take that out of our max expression. And there you have it. You could put that in a proof. Now, I think the proof in the slides does use 4 over m, but does use a different constant value, found a different value during this step of the rough work. And I'm fine with that because there are multiple different values of n that could work as part of this proof.
Where did the plus 1 come from after the max function?
Good question. That's because I sort of skipped a step here. We want n is greater than max This is a bit redundant. I think you already know what I'm saying.
Or
Oh, running out of space again. So yeah, we put +1 because we want to find a specific value of n to complete the proof. And that is an easy way of ensuring that it's greater than the thing we're adding 1 to. So I'll stop there. Good luck on the quiz on Friday, and let me know if you have any questions before then. See y'all.